Hello everyone, welcome to our channel. Today we are going to talk about the interaction between Bose particles. Now, as we know, the Bose particles are subatomic particles with a spin a complete integer like 0, 1, 2, 3, 4 as is written here. For example, photons, alpha particles, and there are other Bose particles. Now, the Bose particles or bosons, they show typical boson particle behavior, and that behavior is an unlimited number of identical particles can occupy the same quantum state. Now let's try to understand it. First of all, we have to understand what is a quantum state. A quantum state is something that contains the entire information about that particle. For example, if we say that we know the quantum state of a particle, then we must know everything about that particle, its momentum, its energy, its spin, its wave function, its space-time coordinates. Whatever information about the particle can exist, it will be in that quantum state. That is quantum state. Now, when we say n bosons can be in the same quantum state, it means that now when we say there are two particles in the same quantum state, it means that those two particles have everything same, like their momentum are same, their energy is same, their spin is same, their wave function is same, their space-time coordinate is same, maybe their temperature is same. Whatever is the information or the information those two particles carry, that is exactly same, which means you cannot distinguish between those two particles, that this one is one and this one is another. They just intertwine with each other. We don't know that which one is who's who, like that. So when n bosons enter in the same quantum state, which means that all the n bosons have everything same: the momentum, energy, spin, wave function, space-time coordinates, anything, any information of those n bosons are same. Positive. Now, a photon, for example, a photon and an alpha particle, they cannot be in the same quantum state. N photons can be in the same quantum state and alpha particles can be in the same quantum state, but a photon and an alpha particle, they cannot be in the same quantum state because the particles are different and the spin is different, so they cannot be in the same quantum state. Now let's take an example. The alpha particle is also a boson, and it's an interesting example. Positive. Now, the alpha particle, as we know, it's a boson. It's an interesting case. See, the alpha particle is made up of proton, proton, and neutron, neutron. Proton and neutron are fermions, those subatomic particles whose spin is half integer, and their behavior is completely different from boson. But here in a combined form, one is a spin up proton, one is a spin down proton, and similarly neutron too. The total spin of the alpha particle becomes 0, which is a full integer, and that makes the alpha particle is made up of fermions, which has completely different behavior than that of boson. But when the total combined spin becomes 0, which is a full integer, it becomes boson, and it shows the typical bosonic behavior of being n particles in same quantum state. Now the typical fermion behavior is that two fermions can never occupy the same quantum state. What is it? Seems like positive for a while. Now, whatever causing the boson-boson interaction means why the n bosons tend to be in the same quantum state. seems to have something to do with the spin of the particle, because if the particle is made up of fermions but the total spin add up to a complete integer, making the particle a boson, its behavior changes and it shows the bosonic behavior. Now for alpha particle, if we increase the temperature or make them too close or increase the energy of the alpha particle, the system, then the whole system, this proton, proton and neutron, neutron, it starts loosening. At large distances and low energies, the alpha particle behaves as boson because this fermion interaction is very small. But at small distances and large energies, the alpha particle stops behaving as boson and it behaves as fermi, as a collection of fermions. Now, this is for the difference between this alpha particle and this proton, proton, neutron, neutron collection. Whenever the energy or temperature or distance changes between two alpha particles, their behavior changes. What changes? The spin of the particle seems to change. When it is in the form of alpha particle, the spin is 0, which is a total integer, and it shows the bosonic behavior. But when we squeeze them together, the fermion interaction acts, its spin became when we make it close, the alpha particles are close at high energy, very few distances, then this proton, neutron, neutron, they act as individually collection of fermions, and then it does not show the bosonic behavior, the typical bosonic behavior. Now this concludes, or maybe I thought that if the interaction between two bosons or the fermions behavior, it's something that depends on the spin. And since there are the two particles, in half the particles are fermion in our world and half are the boson in our world, then only difference that makes the different kind of behavior is the spin of the particle. So could it be that the reason, the cause that is happening between the boson-boson interaction or fermions not to interact with each other, could it be that these two are different aspect of same governing law, some higher governing law which we are not understanding clearly yet? For example, like electromagnetic force, we can see that there is attraction like positive or negative charge, and the similar charge repel, the like charge attracts. Could it be something like that? It's not exactly a force, as we know. There is no change of momentum in this case, so we cannot describe it as a force, but could it be something like it's the same aspect, different aspect of the same governing thing, which depends on the spin. As long as the spin remains half, it behaves as fermion, but as long as the spin combines up to some full integer like 0, 1 or 2, it starts behaving as boson. Posit. Okay. Now, not only the n bosons can occupy the same quantum state, we have also seen, according to the quantum physics theory, that this somehow influences the upcoming photon boson to end up in the same quantum state. It seems, or it originates of some kind of attraction. We are advised not to think of the attractive forces, but yes, it somehow influences so that the upcoming boson end up in the same quantum state where already there are n bosons present. and the probability, as we know, of that boson coming to the quantum state containing n boson is given by this n plus 1. Opposite. Now, so we have found that the interaction between two bosons somehow depends on the spin of the particle, and it also depends the number of n of bosons in a particular quantum state somehow, because higher the number of n in that particular quantum state, higher is the probability of another boson ending up in that particular quantum state. And whatever is causing this interaction, it does not seem of the electromagnetic origin, because, and rather it's a stronger than electromagnetic origin, because when two like alpha particles, it's positively charged. When two alpha particles or n alpha particles will be in the same quantum state, they will show the repulsion, electromagnetic repulsion, but after even feeling the repulsion, they still remains in the same quantum state, which means that something different than that is causing them to stay here. Now, we are habituated to think of a particle like a ball, but in quantum physics we are advised not to think them as a ball. We need to think them as a wave. So in quantum physics, whenever we say the particle or location of the particle, it's not given by a point-like thing. We need to talk about the wave function. And when we say that in a quantum state there are n particles, do not imagine them like n balls compiling up or sitting up in a container, in a box. But even even in a wave function, the amplitude of each particle add up. Like the waves on a string, the number of particles, if n is greater, very greater, think of some very bigger number, like take n is 1 billion or 1 million. Now the wave amplitude, the wave function amplitude of 1 million photons or 1 million bosons will be much lesser than the wave function amplitude of 1 billion bosons. So it somehow seems the attraction is not like a particle or ball colliding, but it's somehow the number of bosons present in a particular quantum state. Somehow we can only tell the attraction thing influences the other upcoming photon to end up in the same quantum state. Pause it for a while. So whatever is causing this interaction is, according to me, some higher order governing law which I haven't understood yet, and I'll try to understand it and I'll come up with later videos of this. Thanks for watching.